Right now, as you're listening to this, roughly 10,000 invisible particles are passing through every square meter of your body every single minute. They're called muons, and here's what should bother you about that. They decay in about 2 millionths of a second. They're born roughly 15 kilometers above your head when cosmic rays slam into the atmosphere. And even traveling at nearly the speed of light, a simple calculation shows they should disintegrate long before they ever reach the ground. They shouldn't make it even 1 kilometer. And yet, they do. Enormous numbers of them reach the surface, pass through buildings, pass through rock, pass through you. Something is allowing a particle that should be dead to survive a journey it has no business completing. And the explanation rewrites what you think you know about time itself. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that might surprise you. You are mostly empty space. The atoms that make up your body, the ones that form your skin, your bones, your brain, are overwhelmingly hollow. The nucleus at the center of each atom is tiny compared to the atom itself. If an atom was scaled up to the size of a football stadium, the nucleus would be a marble sitting at the center of the field. The rest would be empty. And orbiting that marble at enormous distances relative to its size would be electrons. Tiny, almost massless points of negative charge, whipping around in clouds of probability. The electron is probably the most familiar subatomic particle in the world. You've known about it since school? It carries a negative electric charge. It has a very small mass, almost negligibly small compared to the protons and neutrons in atomic nuclei. And it's responsible for almost everything you experience in daily life. When you touch a table and feel it as solid, that's electrons in your hand repelling electrons in the table. When you see light, that's electrons and atoms jumping between energy levels and releasing photons. When electricity flows through a wire, that's electrons moving. Chemistry itself is fundamentally about electrons. Electrons forming bonds between atoms, electrons being shared, electrons being transferred. The electron is a cornerstone of the physical world. And the electron has a secret. It has heavier relatives. Particles that are almost identical to it in every way except mass. They carry the same electric charge. They have the same spin. They interact with the same forces. But they're heavier. Much heavier. And unlike the electron, they don't last. The muon is one of these relatives. It's what physicists call a second-generation charged lepton. Now, that's a lot of jargon, so let me break it down piece by piece, because understanding the classification helps you understand what the muon actually is and why it matters. First, the word lepton. In particle physics, all the fundamental particles of matter are divided into two broad families. There are quarks, which combine in groups of 2 or 3 to form things like protons and neutrons. And there are leptons, which don't combine. They exist on their own as individual particles. The electron is a lepton. It's the lightest charged lepton, and it's completely fundamental. It's not made of smaller parts. You can't split an electron in half. It's one of the basic building blocks of reality. There's no internal structure, no gears inside, no hidden machinery. It's just an electron. A point of charge and mass and spin that exists as a fundamental entity in the universe. Now here's where things get strange. Nature didn't stop at one charged lepton. For reasons that physicists still don't fully understand, nature created 3 generations of charged leptons. 3 versions of essentially the same particle at different masses. It's as if someone designed the electron, decided it worked perfectly, and then, for some unknown reason, built 2 more copies, each one heavier than the last, and each one doomed to self-destruct. There's no obvious reason why the universe needs more than one type of charged lepton. The electron does everything that needs doing. It forms atoms, it enables chemistry, It carries electric current. The heavier versions appear briefly, do very little, and vanish. And yet, the universe insists on having them. The first generation is the electron. It has a mass of about 0.511 mega electron volts, divided by the speed of light squared. In more intuitive terms, the electron is extraordinarily light. It's roughly 1,836 times lighter than a proton. And it's stable. An electron sitting alone in empty space will last forever. It will never decay. It will never break apart. It will sit there for the entire age of the universe and beyond, unchanged. The second generation is the muon. And the muon is where our story centers tonight. The muon carries the exact same electric charge as the electron. -1 elementary charge, it has the same spin, 1/2. It interacts with the same fundamental forces, electromagnetism and the weak nuclear force. In almost every measurable way, the muon behaves exactly like an electron. If you put a muon in a magnetic field, it curves the same way an electron would, just with a slightly different radius because of its different mass. If a muon orbits an atomic nucleus, it forms what's called a muonic atom, and that atom behaves almost identically to a normal atom, just with the muon sitting much closer to the nucleus because of its greater mass. But there's one enormous difference. The muon is about 207 times heavier than the electron. That's not a subtle difference. That's not a small variation. The muon is more than 200 times more massive than its lighter cousin. And it's this extra mass that changes everything about the muon's fate. The third generation is the tau particle. The tau is even heavier than the muon, about 3,490 times heavier than the electron, which makes it roughly 17 times heavier than the muon. The tau is also unstable, even more so than the muon. It decays incredibly quickly, with a mean lifetime of about 2.9 times 10 to the -13 seconds. That's less than a trillionth of a second. The tau barely exists before it's gone. Each of these three charged leptons also has a corresponding neutrino. The electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are also leptons, but they're electrically neutral and nearly massless. They interact so weakly with other matter that trillions of them pass through your body every second without touching a single atom. But the neutrinos aren't our focus tonight. Our focus is the muon. So what exactly is a muon? Physically, a muon is a fundamental particle. Like the electron, it has no internal structure. It's not made of quarks. It's not a composite object held together by some internal force. It's a point particle, a single entity with a specific mass, a specific charge, and a specific spin. If you could somehow hold a muon in your hand and examine it, which you obviously can't because it's far too small and far too short-lived, you would find nothing inside. It's just a muon, a heavier, unstable copy of the electron. The muon's mass is about 105.7 mega electron volts, divided by the speed of light squared. In kilograms, that's about 1.88 times 10 to the -28 kilograms. That's an incredibly small number, unimaginably small by human standards. But in the world of subatomic particles, it's significant. The muon is heavy enough that it can decay into lighter particles, and that's what makes it unstable. Let me explain what instability means for a particle because it's central to everything that follows. When physicists say a particle is unstable, they mean it will spontaneously transform into other, lighter particles after some amount of time. This isn't like a machine breaking down. There are no parts wearing out, no components degrading. The particle simply ceases to exist as itself and becomes something else. The process is governed by the weak nuclear force, one of the four fundamental forces of nature. And the transformation is absolute. The original particle doesn't leave behind a corpse or a fragment. It's gone entirely, and in its place are new particles that didn't exist a moment before. It's not destruction, it's transmutation. The moon doesn't die. It becomes other things. Its energy, its charge, its quantum properties are all conserved, passed on to the daughter particles that emerge from the decay. Nothing is lost. everything is transformed. When a muon decays, it transforms into three particles: an electron, a muon neutrino, and an electron antineutrino. The total charge is conserved. The muon starts with a charge of -1, and the electron carries away that charge of -1. The two neutrinos are electrically neutral, so they don't affect the charge balance. The total energy is also conserved. The muon's mass energy, which is substantial because of its relatively large mass, gets converted into the kinetic energy and mass of the three resulting particles. The electron carries away most of the visible energy, while the neutrinos carry away a significant fraction as well, invisible to most detectors because neutrinos are so difficult to detect. The mean lifetime of a muon is about 2.2 microseconds. A microsecond is a millionth of a second. So 2.2 microseconds is 2.2 millionths of a second. That sounds incredibly short, and it is short by any human standard. If you try to snap your fingers, the entire process from the moment you begin pressing your fingers together to the moment they slip past each other and produce a sound takes roughly a few hundredths of a second. In that time, more than 10,000 muon lifetimes would have elapsed. A muon born at the start of your finger snap would have decayed and vanished long before the snap was complete. In the time it takes you to blink, roughly 300 to 400 milliseconds, about 150,000 muon lifetimes would pass. Every single one of those muons would have been born, lived its entire existence, and decayed into an electron and two neutrinos before your eyelid finished closing. That's how brief a muon's life is. It exists for a duration so short that no human sense could ever register it. No camera could capture it in a single frame. No stopwatch could measure it without specialized electronic equipment. But in the world of particle physics, 2.2 microseconds is actually a relatively long lifetime. Many particles decay far faster. The tau, as I mentioned, lives for less than a trillionth of a second. Charged pions, which we'll talk about later, live for about 26 nanoseconds, which is 26 billionths of a second. Neutral pions live for less than a tenth of a femtosecond, which is so short that the particle barely travels the width of an atomic nucleus before it's gone. Compared to these particles, the muon is practically long-lived. Its 2.2 microsecond lifetime is about 85 times longer than a charged pion's lifetime, and billions of times longer than a neutral pion's. In the frenetic world of subatomic particles, where most unstable particles vanish almost the instant they're created, the muon is remarkably persistent. This relative persistence is one of the reasons the muon plays such an outsized role in the story we're exploring tonight. If muons decayed as fast as most other unstable particles, they would never come close to reaching the ground. Even the remarkable effects of relativity couldn't stretch their lifetimes enough. It's precisely because the muon lives relatively long by particle standards that the effects of time dilation become so dramatic and so measurable. Now, let me address a question that has puzzled physicists for decades, and in many ways still does. Why does the muon exist at all? This isn't a rhetorical question. It's one of the deep unsolved problems in particle physics. When the muon was first discovered in the late 1930s, nobody expected it. Nobody predicted it. Physicists at the time were looking for a completely different particle. They were looking for the particle that Hideki Yukawa had predicted in 1935, a particle that would mediate the strong nuclear force, holding protons and neutrons together in atomic nuclei. Yukawa had calculated that this particle should have a mass of roughly 200 times the electron mass, which was suspiciously close to the mass of the muon. So when experimenters found a particle with about the right mass in cosmic ray experiments, everyone assumed it was Yukawa's particle, but it wasn't. The muon didn't interact strongly with atomic nuclei the way Yukawa's particle should. Experiments in the 1940s showed that muons pass through matter far too easily. If they were really the carriers of the strong force, they should have been absorbed by nuclei almost immediately upon encountering them. Instead, muons sailed right through, interacting hardly at all. The key experiment was performed in 1946 by Marcello Conversi, Ettore Pancini, and Oreste Piccioni in Rome. They showed that negatively charged muons in carbon were not captured by the nucleus quickly enough to be the strongly interacting particle Yukawa had predicted. A true strong force carrier should have been swallowed by a carbon nucleus almost instantly. The muon wasn't. It lingered, orbiting the nucleus like a heavy electron before eventually decaying. This was deeply confusing. The physicist Isidore Isaac Rabi famously reacted to the discovery with the question, who ordered that? It was a joke, but it captured a genuine frustration. The muon seemed to serve no purpose. It wasn't needed for atoms. It wasn't needed for nuclei. It didn't hold anything together. It was just there. A heavier version of the electron with no obvious reason to exist. Yukawa's particle was eventually found separately. It's called the pion, and it's a very different kind of particle from the muon. The pion is made of quarks. It's a composite particle, not fundamental, and it does interact strongly with nuclei. The pion was identified in 1947, a decade after the muon had been mistaken for it. This discovery clarified the situation, but only deepened the mystery of the muon. If the muon wasn't Yukawa's particle, what was it? Why did nature bother creating a heavier copy of the electron? We still don't have a fully satisfying answer. The standard model of particle physics, which is our best theory of fundamental particles and forces, accommodates the muon perfectly. The mathematics of the standard model requires 3 generations of leptons. Without all 3 generations, certain symmetries of the theory wouldn't work, and certain predictions wouldn't match observation. In fact, having exactly 3 generations turns out to be deeply connected to the existence of matter in the universe. A mathematical property called CP violation, which describes a subtle asymmetry between matter and antimatter, depends on having at least 3 generations of fundamental particles. Without this asymmetry, the Big Bang would have produced equal amounts of matter and antimatter, all of which would have annihilated, leaving behind nothing but radiation. No stars, no planets, no life. It's a profound irony. The muon, a particle that seemed to serve no purpose when it was discovered, may be part of the reason the universe contains matter at all. But saying the mathematics requires it isn't the same as understanding why nature chose this particular structure. Why 3 generations? Why not 2? Why not 5? Why do the generations have the specific masses they do? These are open questions. Some physicists believe the answers lie in a deeper theory beyond the standard model, a theory we haven't discovered yet. Others think we might never know. The muon exists, it has the properties it has, and the universe is the way it is. What we do know is that the muon is real, it's fundamental, and it's everywhere. Well, not everywhere in the universe in equal amounts. Muons are constantly being created in Earth's atmosphere, as we'll explore in detail, but they're also created in particle accelerators, in supernova explosions, in any environment where enough energy is concentrated in a small enough space to produce particles with a muon's mass. The energy required is about 106 mega-electron volts, which is a lot by everyday standards but modest by the standards of high-energy physics. Let me tell you something remarkable about how precisely we know the muon's properties, because it illustrates how important this particle has become to modern physics. The muon's magnetic moment, which describes how it behaves in a magnetic field, has been measured to extraordinary precision. Physicists have measured a quantity called the muon's anomalous magnetic moment, often written as G-2, to a precision of better than 1 part per million. That's like measuring the distance from New York to Los Angeles and getting it right to within a few meters. A few steps of error over a journey of 4,000 kilometers. It's an almost absurdly precise measurement. This measurement matters enormously because the standard model also predicts the muon's anomalous magnetic moment with extraordinary precision. If the measurement and the prediction agree, it confirms our understanding of particle physics. If they disagree, it could be a sign of new physics, new particles, or new forces that we haven't discovered yet. For years, there was a tantalizing discrepancy between the measured value and the predicted value. The measurement, carried out at Brookhaven National Laboratory and later at Fermilab, consistently gave a value slightly different from the standard model prediction, generating enormous excitement that something beyond the standard model might be influencing the muon's behavior. As of the most recent results, the situation remains one of the most closely watched in all of particle physics. But regardless of how this puzzle resolves, the fact that the muon's properties are measured and calculated to such extraordinary precision shows how central this particle has become to our understanding of the fundamental laws of nature. The muon is also remarkably useful as a practical tool. Because muons are produced in enormous quantities in the atmosphere, and because they penetrate deeply through matter, they can be used as a kind of natural imaging tool. This technique is called muon tomography, and it works on the same basic principle as a medical X-ray, but with muons instead of X-ray photons. When muons pass through dense material, they're deflected slightly by the electric fields of atomic nuclei. The denser the material, the more the muons are deflected. By placing muon detectors around an object and measuring how muons are scattered or absorbed as they pass through, you can build up a three-dimensional image of the object's internal structure without ever opening it up or cutting into it. This technique has been used for some fascinating applications. In 2017, physicists used muon tomography to discover a previously unknown large void inside the Great Pyramid of Giza. The pyramid is about 4,500 years old, and archaeologists had been studying it for centuries. But muons revealed a hidden chamber roughly 30 meters long that no one had known about. The muons passed through the pyramid, and the detectors measured how many arrived on the other side. Regions with less stone, like empty chambers, allowed more muons through. Regions with solid stone absorbed or deflected more muons. By carefully analyzing the pattern, the researchers mapped out the interior structure and found the void. Muon tomography has also been used to image the inside of volcanoes, to scan shipping containers for hidden nuclear materials, and to inspect the damaged reactors at Fukushima in Japan after the 2011 nuclear disaster. In each case, the muons doing the imaging were the very same atmospheric muons we're talking about tonight. Particles born high in the atmosphere from cosmic ray collisions, traveling down to the surface and passing through whatever structures happen to be in their path. The muon's ability to penetrate deeply through matter is a consequence of its mass and the nature of its interactions. The muon is much heavier than the electron, so it's not deflected as easily when it passes near atomic nuclei. Think of it like throwing a bowling ball versus throwing a ping pong ball at a set of obstacles. The bowling ball plows through more easily because its greater mass gives it more momentum. Similarly, a muon with the same kinetic energy as an electron will plow through matter more effectively, because its greater mass makes it harder to deflect. The muon also doesn't interact through the strong nuclear force. This means it doesn't get absorbed by atomic nuclei the way protons or neutrons would. It simply passes by them, feeling only the electromagnetic force and the weak force. The electromagnetic interaction can deflect it slightly, and the weak interaction allows it to eventually decay, but neither force stops it quickly. A high-energy muon can pass through hundreds of meters of rock before it either decays or loses enough energy to stop. This penetrating power is part of what makes the muon so remarkable. Right now, muons are passing through the ceiling above you, through the floor beneath you, through the walls around you. If you're in a building, muons are passing through every floor, every wall, every piece of furniture. If you're underground, muons are passing through meters of soil and rock to reach you. Every person on the planet is being constantly traversed by muons, and nobody feels a thing. No sensation, no warmth, no tingling. The muons pass through the atoms of your body without disturbing them in any meaningful way, like a ghost walking through a wall. You have never experienced a moment in your life without muons passing through you. Not when you were born, not when you were sleeping, not right now as you listen to this. They are always there, invisible and silent, and utterly unnoticed. The only way to significantly reduce the number of muons reaching you would be to go very deep underground, hundreds of meters beneath the surface, where the overlying rock finally absorbs enough of them to make a noticeable difference. This is why some particle physics experiments that need extremely low background radiation are located deep underground in mines or tunnels. The Super Kamiokande neutrino detector in Japan sits 1,000 meters below the surface inside an old zinc mine. The Sudbury Neutrino Observatory in Canada was located 2 kilometers underground in a nickel mine. At those depths, the muon flux is reduced by a factor of 1,000,000 or more compared to the surface. These experiments are hiding from the relentless rain of atmospheric muons, burrowing deep into the Earth to escape the very particles we're discussing tonight. And this brings us to the essential tension of our story. These muons, the ones passing through you right now, were born high in the atmosphere. 15 kilometers up, maybe 20, maybe even 30. They were created in violent collisions between cosmic ray particles and atmospheric molecules, and they have a mean lifetime of 2.2 microseconds, a mere 2.2 millionths of a second. The mathematics of classical physics says they shouldn't be here. They should have decayed long before reaching the ground. The journey from their birthplace in the upper atmosphere to the surface should take far longer than their fleeting lifetime allows. And yet, here they are, passing through your body at this very moment. Thousands of them every minute. Something extraordinary is happening to these particles during their journey. Something that stretches their lifetimes, or shrinks their distances, or both. Something that makes the impossible routine. And to understand what that something is, we first need to understand where these muons come from, and how they're born. Because the story of the muon's origin in Earth's atmosphere is itself a remarkable tale. A tale of unimaginable violence, happening silently, invisibly, miles above your head, every second of every day. Cosmic rays, particles accelerated to energies that dwarf anything humans have ever achieved in a laboratory, are slamming into the thin upper reaches of our atmosphere at nearly the speed of light. And when they hit, they create cascades of particles, showers of debris that rain down through the atmosphere, transforming and decaying and transforming again as they fall. The muons that reach you are the survivors of this cascade, the remnants of a chain of events that began in deep space, perhaps millions or billions of years ago, when a proton was flung from an exploding star or a spinning black hole and sent hurtling across the galaxy at nearly the ultimate speed. The story of where muons come from is the story of the most energetic natural process that touches Earth's surface on a daily basis. It's a story that connects the most distant and violent objects in the universe to the particles passing through your body at this very moment. And that story begins not with the muon itself, but with what strikes the top of our atmosphere from above. Every second of every day, Earth is under bombardment. Not from asteroids, not from debris, from particles. Subatomic bullets traveling at nearly the speed of light, arriving from every direction in space, slamming into the thin upper reaches of our atmosphere with energies that would seem absurd if they weren't real. These particles are called cosmic rays, and they are the reason muons exist in the atmosphere at all. Without cosmic rays, there would be no muons raining down on the surface, no invisible particles threading through your body, no mystery about how a short-lived particle reaches the ground. The muon story begins not on Earth, but in the most violent environments the universe has to offer. It begins with the question of what cosmic rays are, where they come from, and what happens when they hit the atmosphere at unimaginable speeds. A cosmic ray is not actually a ray at all. The name is a historical artifact from the early 20th century, when scientists first detected mysterious ionizing radiation coming from the sky and assumed it was some form of electromagnetic radiation, like gamma rays or X-rays. It's not. A cosmic ray is a particle. Specifically, it's a high-energy atomic nucleus, stripped of its electrons, hurtling through space at tremendous speed. About 89% of cosmic rays are protons, which are just hydrogen nuclei. About 10% are alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons bound together. The remaining roughly 1% consists of heavier nuclei, everything from carbon and oxygen to iron, and occasionally even heavier elements. There are also small numbers of electrons and positrons in the cosmic ray flux, but the overwhelming majority are protons. These particles have been accelerated to extraordinary energies by some of the most powerful and violent processes in the universe: exploding stars, collapsing magnetic fields, jets from supermassive black holes. The lowest energy cosmic rays, those with energies comparable to what particle accelerators on Earth can produce, come primarily from the Sun. Solar cosmic rays are produced during solar flares and coronal mass ejections, when the Sun's magnetic field violently reconfigures itself and flings charged particles outward at high speeds. These solar energetic particles can have energies up to a few billion electron volts, which sounds impressive but is actually modest by cosmic ray standards. Solar cosmic rays are the weakest members of the family. The next tier comes from within our galaxy. Galactic cosmic rays are produced by supernova remnants, the expanding shells of gas and debris left behind when massive stars explode at the end of their lives. When a star goes supernova, it releases an almost inconceivable amount of energy, roughly 10 to the 46 joules, in a single event. That's more energy than the Sun will produce in its entire 10 billion year lifetime, all released in a matter of seconds. The shock wave from this explosion expands outward at thousands of kilometers per second, plowing into the surrounding interstellar gas and creating a turbulent, magnetized environment. Charged particles, protons, and heavier nuclei can get caught in these shock waves. As the shock wave moves through space, particles bounce back and forth across it, gaining energy with each crossing. This process is called diffusive shock acceleration, or Fermi acceleration, named after physicist Enrico Fermi, who first proposed the mechanism. Each time a particle crosses the shock wave, it picks up a little more energy. Over thousands or millions of crossings, the particle accumulates enormous kinetic energy. It's like a ping-pong ball bouncing between two walls that are slowly moving toward each other. Each bounce gives the ball a little more speed. Given enough bounces, the ball ends up moving incredibly fast. The process is slow but relentless, and a supernova remnant can maintain its shockwave for tens of thousands of years, giving particles ample time to accumulate energy. Supernova remnants can accelerate particles to energies of up to about 10 to the 15 electron volts, which is called a peta-electron volt. That's a million billion electron volts concentrated in a single proton. An extraordinary amount of energy for a single subatomic particle, more than enough to be detected by instruments, and far beyond anything the particle started with before the supernova shockwave got hold of it. These are the workhorses of the cosmic ray spectrum, the particles that make up the vast majority of cosmic rays bombarding Earth's atmosphere. But even this isn't the upper limit. The highest energy cosmic rays, the most extreme particles ever detected, have energies that go far beyond what supernova remnants can produce. These ultra-high energy cosmic rays have energies exceeding 10 to the 18 electron volts, and in rare cases, even 10 to the 20 electron volts. The most famous example is a particle detected on October 15th, 1991, by the Fly's Eye detector in Utah. This particle, nicknamed the Oh My God particle, had an energy of about 3 times 10 to the 20 electron volts. To put this in perspective, this was a single proton carrying the same kinetic energy as a baseball, thrown at about 96 kilometers per hour. All the energy of a thrown baseball concentrated in a single subatomic particle. The particle was moving at 99.9999999999999999999999999999999% of the speed of light. That's so close to the speed of light that the difference is almost meaningless. If this proton and a photon of light started a race across the observable universe, the proton would arrive only about 4 kilometers behind the photon after traveling 93 billion light years. 4 kilometers out of 93 billion light years. That's how close to light speed this particle was moving. Nobody knows for certain what accelerates particles to these extreme energies. Supernova remnants can't do it. Their shock waves aren't powerful enough. The leading candidates are active galactic nuclei, the supermassive black holes at the centers of galaxies that are actively consuming matter and producing enormous jets of energy, and gamma ray bursts, the most energetic explosions in the universe. Some physicists have also proposed that ultra-high energy cosmic rays might come from exotic processes we don't fully understand, perhaps involving the decay of hypothetical super heavy particles left over from the early universe. But whatever their source, these particles exist. They've been detected. They're real. Now, here's the key point for our story. These cosmic ray particles, whether they're modest solar protons or ultra-high energy monsters from distant galaxies, are constantly hitting Earth's atmosphere. The flux is enormous. About 10,000 cosmic ray particles strike every square meter of the top of Earth's atmosphere every second. Most of these are the lower energy galactic cosmic rays, protons with energies in the billions of electron volts. The ultra-high energy particles are incredibly rare. You might get 1 per square kilometer per century at the highest energies, but the garden variety galactic cosmic rays are plentiful. They arrive from all directions, day and night, rain or shine, without pause. Earth has been bathed in this cosmic radiation for its entire existence. It was raining down on the dinosaurs. It was raining down on the first living cells. It's raining down on you right now. So, what happens when one of these cosmic ray protons hits the atmosphere? This is where the story gets violent, and this is where muons are born. Earth's atmosphere is a blanket of gas about 100 kilometers thick, though most of the mass is concentrated in the lowest 20 kilometers. At the top of the atmosphere, the air is incredibly thin, almost a vacuum. But even this thin gas presents a target for incoming cosmic rays. A cosmic ray proton traveling at nearly the speed of light doesn't have to go far before it encounters an atomic nucleus. The atmosphere is made mostly of nitrogen, about 78%, and oxygen, about 21%, with small amounts of argon and other gases. Nitrogen nuclei contain 7 protons and 7 neutrons. Oxygen nuclei contain 8 protons and 8 neutrons. These are the targets that cosmic ray protons smash into. The first collision typically occurs at an altitude of about 15 to 35 kilometers above the surface, depending on the energy of the incoming cosmic ray and the angle at which it enters the atmosphere. Higher energy cosmic rays tend to penetrate slightly deeper before their first interaction, because they have more momentum and are slightly harder to deflect. But most first collisions happen in the stratosphere, roughly 20 to 30 kilometers up. And when the collision happens, it's spectacular. Not in a way you can see with your eyes, but spectacular in terms of what's produced. The incoming proton, carrying billions or trillions of electron volts of kinetic energy, strikes a nitrogen or oxygen nucleus. The collision is so violent that neither the proton nor the target nucleus survives intact. They're both shattered. The enormous kinetic energy of the cosmic ray is converted into mass and motion through Einstein's famous relationship between energy and mass. New particles are created out of pure energy, dozens of them, sometimes hundreds. This is one of the most remarkable facts in physics. Energy can become matter. If you concentrate enough energy into a small enough space, new particles simply appear. They materialize out of the collision energy as if conjured from nothing. They're not coming from inside the proton or the nucleus. They're being created fresh, assembled from the energy of the impact, according to the rules of quantum field theory. The more energy available in the collision, the more particles can be created, and the heavier those particles can be. The dominant particles produced in these atmospheric collisions are pions. Pions come in 3 varieties: positive pions, negative pions, and neutral pions. Pions are not fundamental particles. They're made of quarks, specifically a quark and an antiquark bound together by the strong nuclear force. They're among the lightest particles that contain quarks, which is why they're the most easily produced in these collisions. So, when a cosmic ray smashes into an atmospheric nucleus and produces a spray of new particles, most of those particles are pions. A typical high-energy cosmic ray collision might produce 10, 20, or even 30 pions in a single interaction, along with fragments of the shattered nucleus, and occasionally other particles like kaons. The exact number depends on the energy of the incoming cosmic ray. Higher energy collisions produce more particles, but the pions are the dominant product, and they're the critical link in the chain that leads to muons. Here's what happens next, and it happens fast. The neutral pions decay almost immediately. A neutral pion has a mean lifetime of about 8.4 times 10 to the negative 17 seconds. That's 84 millionths of a trillionth of a second. It's so brief that a neutral pion traveling at the speed of light would cover only about 25 nanometers before decaying. That's roughly the width of a single virus. The neutral pion essentially decays the instant it's created, transforming into 2 gamma-ray photons. These gamma-ray photons are extremely high energy, and they go on to produce their own cascades through a process called pair production, where a gamma ray converts into an electron and a positron near an atomic nucleus. Those electrons and positrons then produce more gamma rays through a process called bremsstrahlung, which is radiation emitted when a charged particle is deflected by a nucleus, and those gamma rays produce more pairs and so on. This creates what physicists call an electromagnetic cascade, a shower of electrons, positrons, and gamma rays that multiplies as it descends through the atmosphere. These electromagnetic showers are important for understanding cosmic rays, but they're not where our muons come from. Our muons come from the charged pions, the positive pions and negative pions, and this is where the chain becomes beautiful in its simplicity. A charged pion has a mean lifetime of about 26 nanoseconds. 26 billionths of a second. That's about 300 million times longer than a neutral pion's lifetime, but still extraordinarily short by any human standard. In those 26 nanoseconds, a charged pion traveling near the speed of light can cover roughly 8 meters. After that, it decays, and here's the crucial fact. A charged pion decays almost exclusively into a muon and a muon neutrino. This is the birth of a muon. A positive pion transforms into a positive muon and a muon neutrino. A negative pion transforms into a negative muon and a muon antineutrino. The process is clean, elegant, and nearly 100% efficient. Roughly 99.99% of charged pion decays produce a muon. There's almost no other option. The pion's mass and quantum numbers constrain the decay so tightly that the muon channel is essentially the only one available. This means that every charged pion produced in a cosmic ray collision becomes a muon. And since cosmic ray collisions produce large numbers of charged pions, they also produce large numbers of muons. The pion is the factory. The cosmic ray is the power source, and the atmosphere is the factory floor. But the chain doesn't stop with the first collision. The secondary particles produced in the first collision, including pions and nuclear fragments, still have enormous energy. Many of them are traveling at nearly the speed of light themselves. When these secondary particles encounter more atmospheric nuclei deeper in the atmosphere, they can trigger additional collisions. Those collisions produce more pions, which produce more muons. And the particles from those secondary collisions can trigger tertiary collisions, and so on. The result is a cascade, a shower of particles that multiplies as it descends through the atmosphere. What started as a single cosmic ray proton becomes a broad spray of thousands of particles spreading downward and outward through the atmosphere like an inverted tree with branches splitting again and again. Physicists call these extensive air showers. The term was coined by the French physicist Pierre Auger, who in 1938 set up particle detectors separated by distances of up to 300 meters in the Swiss Alps and noticed that they sometimes triggered simultaneously. He realized that the detections couldn't be from separate particles arriving independently by coincidence. The coincidences were too frequent and too precise. They had to be from a single cosmic ray event, a single primary particle whose cascade had spread out over a wide area. This was the first direct evidence that cosmic ray interactions produce these enormous showers of secondary particles. Auger estimated that the primary cosmic rays responsible for the largest showers he observed must have energies exceeding 10 to the 15 electron volts, a number that astonished the physics community at the time. No one had imagined that nature could accelerate individual particles to such extreme energies. Modern experiments have mapped these air showers in extraordinary detail. The Pierre Auger Observatory in Argentina, which covers 3,000 square kilometers of the Argentine pampas, with over 1,600 particle detectors and 27 fluorescence telescopes, can detect showers produced by the highest energy cosmic rays. A single ultra-high energy cosmic ray can produce a shower containing billions of particles spread over an area of several square kilometers by the time it reaches the ground. These showers develop over microseconds as the cascade propagates downward through the atmosphere, growing and multiplying, and then gradually dying as the particles lose energy and are absorbed. Within these showers, there are different components. There's the electromagnetic component, the electrons, positrons, and gamma rays produced by neutral pion decays. There's the hadronic component, the surviving protons, neutrons, pions, and other strongly interacting particles that continue to collide and produce more secondaries. And there's the muonic component, the muons produced by charged pion decay. The muonic component is particularly important because muons, once created, are extremely difficult to stop. Unlike the electromagnetic particles, which are relatively easily absorbed by the atmosphere, and unlike the hadronic particles, which continue to interact and lose energy through nuclear collisions, muons just keep going. They don't interact through the strong force, so they don't get tangled up in nuclear collisions. They're too heavy to lose energy quickly through electromagnetic radiation like electrons do. They just barrel downward through the atmosphere, losing energy slowly through ionization, the process of knocking electrons off atoms they pass near. This is why muons dominate the cosmic ray flux at ground level. The electromagnetic and hadronic components of the shower are mostly absorbed by the atmosphere before reaching the surface. The electromagnetic particles are absorbed in the upper atmosphere, their energy dissipated through successive interactions. The hadronic particles interact with atmospheric nuclei and are gradually broken down into lighter fragments. But the muons survive. They punch through the atmosphere like bullets through fog. By the time the shower reaches sea level, most of what remains is muons and neutrinos. The neutrinos pass through the Earth entirely, completely invisible to almost any detector. The muons are the main detectable component that reaches the ground, and the numbers are staggering. At sea level, roughly 10,000 muons pass through every square meter of horizontal surface every single minute. That's about 166 muons per square meter per second. Think about the area of your outstretched hand. It's roughly 150 square centimeters, or about 0.015 square meters. Every second, roughly 2 or 3 muons pass through your hand. In a minute, about 25. In an hour, roughly 1,500. In a day, about 36,000 muons pass through an area the size of your palm. You've never felt a single one. Across the entire surface of Earth, which has an area of about 5.1 times 10 to the 14 square meters, the total muon flux is roughly 10 to the 18 muons per minute. That's about 1 billion muons striking the Earth's surface every 60 seconds. This is an enormous number. It represents a constant, invisible rain of subatomic particles, a rain that has been falling for as long as Earth has existed. A rain that will continue as long as there are cosmic rays and an atmosphere for them to hit. The energy spectrum of these muons is also worth understanding because it matters for the puzzle we're building toward. Not all muons arrive at the surface with the same energy. Most ground-level muons have energies in the range of a few billion electron volts. The average energy is roughly 3 to 4 billion electron volts, which corresponds to speeds above 99.9% of the speed of light. That's incredibly fast. At 99.8% of light speed, a muon would cross the entire continental United States in about a 50th of a second. These are not slow-moving particles gently drifting down from the sky. They're screaming through the atmosphere at relativistic speeds, covering the full depth of the atmosphere in a tiny fraction of a second. Some muons have even higher energies, reaching into the hundreds of billions or even trillions of electron volts. These ultra-high energy muons are produced by the most energetic cosmic ray events, and they can penetrate deep underground. The highest energy muons can pass through kilometers of rock before losing enough energy to stop. These are the muons that occasionally trigger detectors in deep underground laboratories, the rare stragglers from particularly powerful cosmic ray showers that manage to push particles deep into the Earth. But most muons at the surface are in that few billion electron volt range. Fast, energetic, but not extreme. And it's these typical muons that present the puzzle most clearly. Let's take a conservative example. A muon at the lower end of the energy spectrum, traveling at 99.8% of the speed of light. Because even at this speed, even with all that energy, even with the muon's relatively long lifetime compared to other unstable particles, the simple arithmetic doesn't work. Let me paint the picture more concretely. A cosmic ray proton arrives from deep space, traveling at nearly the speed of light. It hits a nitrogen nucleus at an altitude of, say, 15 kilometers above sea level. The collision produces a spray of particles, including several charged pions. One of those pions, a negative pion, flies downward at close to the speed of light. After about 26 nanoseconds, it decays into a negative muon and a muon antineutrino. The muon is born at an altitude of, say, 14 kilometers, give or take. It inherits most of the pion's energy and continues downward at roughly 99.8% of the speed of light. The muon has a mean lifetime of 2.2 microseconds. It has 14 kilometers of atmosphere to traverse before reaching the ground, and it's moving at nearly the speed of light. A quick calculation shows it can travel only about 660 meters before decaying on average, less than a kilometer. And it needs to cover 14,000 meters. The distance is more than 21 times farther than its lifetime should allow, even at nearly the speed of light. And yet, what we actually observe is completely different. Instead of essentially no muons reaching sea level, we measure roughly 10,000 per square meter per minute. They're everywhere, in every detector, on every mountaintop, at every beach, and every rooftop, and every basement. The muons are reaching the ground in enormous numbers, as casually and as reliably as rain falling from a cloud. Something is catastrophically wrong with the simple calculation. The math says the muons can't make it. Reality says they do. Every second, every minute, every day. The resolution to this puzzle doesn't involve any new particles, any new forces, any exotic or speculative physics. It involves something that had already been worked out decades earlier by a patent clerk in Bern, Switzerland. Something that most people had thought of as abstract and disconnected from everyday reality. A theoretical framework that describes what happens to space and time when objects move at speeds approaching the speed of light. The answer was already there, waiting in the equations of special relativity. And the muon, this unstable particle that shouldn't survive its journey to the ground, was about to become one of the most elegant and convincing proofs that those equations describe reality. Let's slow down and really sit with this problem, because the numbers deserve more attention than a passing glance. What we're dealing with here isn't a minor discrepancy. It's not a situation where the prediction is a little bit off and maybe some adjustment or correction could fix it. This is a situation where the prediction is wrong by a factor of billions. The classical calculation says that essentially no muons should survive the journey from the upper atmosphere to the ground. The observation says that roughly 10,000 muons reach every square meter of Earth's surface every single minute. These two facts are completely, irreconcilably incompatible if you assume that a muon's clock ticks at the same rate no matter how fast it's moving. So let's walk through the calculation more carefully, step by step, to make sure we haven't made an error. Let's be rigorous about this, because when a prediction fails this badly, you want to be certain that the prediction was fair before you throw out the underlying assumptions. Start with what we know. A muon is created when a charged pion decays in the upper atmosphere. The pion itself was produced in a collision between a cosmic ray and an atmospheric nucleus, typically at an altitude somewhere between 15 and 35 kilometers. Most muon production happens around 15 to 20 kilometers above sea level. Let's use 15 kilometers as a representative altitude because it's the lower end of the production zone and therefore the most generous assumption. If we used 20 or 30 kilometers, the problem would only get worse. The muon inherits most of the energy of the pion that produced it, and because that pion came from a high-energy cosmic ray collision, the muon is moving fast. Extremely fast. The typical muon detected at sea level has an energy of a few billion electron volts, corresponding to speeds above 99.9% of the speed of light. Some muons are faster. Some are a bit slower. For this calculation, let's use a conservative figure of 99.8%, representing the lower end of the energy range. Even at this speed, the numbers fail catastrophically. The speed of light is approximately 300,000 kilometers per second. At 99.8% of that, the muon is traveling at roughly 3 times 10 to the 8th meters per second. The small rounding doesn't change the argument in any meaningful way. Now, the muon has a mean lifetime of 2.2 microseconds. This has been measured with great precision in laboratories where muons are produced at rest or at low speeds. The value is about 2.196898 microseconds to be precise, but 2.2 is accurate enough for our purposes. This is the average time a muon exists before it decays into an electron and 2 neutrinos. Some muons live a little longer, some a little shorter, but on average they last 2.2 millionths of a second. How far can a muon travel in 2.2 microseconds at 99.8% of the speed of light? Multiply the speed by the time. 3 times 10 to the 8th meters per second multiplied by 2.2 times 10 to the negative 6 seconds gives 660 meters. That's the average distance a muon should cover before decaying. 660 meters, less than a kilometer. About the length of 6.5 football fields, laid end to end. The muon needs to travel 15,000 meters. It can travel, on average, 660 meters. The distance is roughly 23 times the muon's expected travel range. That alone should tell you the muon isn't going to make it. But let's be more precise about exactly how badly the numbers fail, because exponential decay has a specific mathematical structure that lets us calculate the survival probability at any distance. Radioactive decay, whether we're talking about muons or uranium or any other unstable particle, follows an exponential law. The number of particles surviving after a time t is given by the original number multiplied by e raised to the power of negative t divided by the mean lifetime. The constant e is Euler's number, approximately 2.718. This exponential function drops off steeply. After one mean lifetime, about 36.8% of the original particles remain. After 2 mean lifetimes, about 13.5%. After 3, about 5%. After 4, about 1.8%. After 5, about 0.7%. The fraction drops by roughly a factor of e, or about 2.72, with each additional lifetime. This is a relentless, merciless mathematical function. It doesn't plateau, it doesn't level off, It just keeps cutting the surviving population down by the same fraction with every passing lifetime. The curve plunges downward like a cliff, each step lower than the one before, until the number of survivors becomes vanishingly small. It's the mathematics of inevitability. Given enough time, everything unstable disappears. For our muon, the relevant quantity isn't really time but distance. Since the muon is traveling at a constant speed, time and distance are directly related. The distance corresponding to one mean lifetime at 99.8% of the speed of light is 660 meters. So we can express the survival probability as a function of distance traveled. After 660 meters, 36.8% survive. After 1,320 meters, about 13.5% survive. After 1,980 meters, about 5%, and so on. At 15,000 meters, the number of mean lifetime lengths the muon has traversed is 15,000 divided by 660, which is about 22.7. Call it roughly 23 lifetimes. The survival fraction after 23 lifetimes is raised to the negative 23. Pull out a calculator and compute that. The answer is approximately 1.03 times 10 to the negative 10. That's about 1 in 10 billion. One muon out of every 10 billion created at 15 kilometers altitude would survive long enough to reach sea level under classical assumptions. Now let's put that in context. The cosmic ray flux produces a large number of muons in the upper atmosphere, but not 10 billion per square meter per minute. The actual production rate at altitude is perhaps a few tens of thousands of muons per square meter per minute in the relevant energy range. If 1 in 10 billion of those survives, the expected flux at sea level would be a tiny fraction of a single muon per square meter per minute, effectively zero. You would need to wait for enormous periods of time, thousands or millions of minutes, to detect even one muon reaching the ground from this altitude in a detector of modest size. And yet the measured flux is 10,000 per square meter per minute. The ratio between what we observe and what classical physics predicts is staggering. We're not off by a factor of 2 or 10 or even 100. We're off by a factor of roughly 100 billion. The discrepancy is so vast that no minor adjustment or clever correction to the calculation could fix it. You can't tweak the production altitude, or the muon's energy, or the exact value of the mean lifetime by enough to make the numbers work. The fundamental structure of the prediction is wrong. Something about the underlying assumptions must be incorrect. At this point, you might be wondering whether there's some clever way to rescue the classical picture. Maybe the muons aren't really created at 15 kilometers. Maybe they're created much lower, closer to the ground, where they wouldn't need to survive as long. Or maybe there's some mechanism that produces new muons at lower altitudes, replenishing the supply as the originals decay. Or maybe the muon's lifetime isn't really 2.2 microseconds when it's moving fast. Maybe there's some effect of speed on the particle's stability that makes it last longer without invoking relativity. Let's consider each of these possibilities because ruling them out is important. It's not enough to say the classical prediction fails. We need to understand why the obvious escape routes don't work. First, could the muons be created at lower altitudes? The answer is no, and we know this conclusively from direct observation. Physicists have measured the cosmic ray flux at various altitudes using detectors carried aloft by balloons, aircraft, and even strapped to the outside of rockets. These measurements go back to the 1930s, when physicists like Erich Wegener in Germany and others launched instruments into the stratosphere on unmanned balloons to study the intensity of cosmic radiation at different heights. The measurements are clear and have been repeated hundreds of times since then, with increasingly sophisticated equipment. The rate of production of secondary particles, including pions, and the muons they decay into, peaks at altitudes of about 15 to 20 kilometers. This altitude is sometimes called the Pfotzer maximum, named after Georg Pfotzer, who first identified it in 1936. Below this altitude, the secondary particle flux decreases as particles are absorbed by the increasingly dense atmosphere. Above it, the flux also decreases because there isn't enough atmospheric material to serve as targets for cosmic ray collisions. The production zone is high up, and this is not a matter of debate. It's one of the best established facts in cosmic ray physics. This makes sense physically. The atmosphere at those altitudes is thick enough to provide targets for cosmic ray collisions, but thin enough that the secondary particles haven't yet been absorbed. At lower altitudes, the atmosphere is denser. Secondary particles produced at lower altitudes tend to interact with atmospheric nuclei before they can decay into muons. The pions, which have very short lifetimes and also interact through the strong force, are particularly vulnerable to being absorbed before they can decay. The pion to muon conversion is most efficient at high altitudes, where the air is thin enough for the pions to decay in flight, rather than being swallowed by another nucleus. So the production zone really is high up. The muons are born high, and they need to travel a long way to reach the ground. Second, could new muons be created at lower altitudes, replacing the ones that decay? This does happen to some degree. Cosmic ray showers are complex, and secondary collisions at various altitudes do produce additional pions and therefore additional muons. But this effect is already accounted for in the standard models of cosmic ray propagation through the atmosphere. Even when you include all the secondary production, the predicted muon flux at sea level is still far too low to match what's observed. The problem isn't that we're underestimating muon production, it's that the muons are surviving far longer than they should. Third, could the muon's lifetime change when it's moving fast, through some mechanism that doesn't involve relativity? This is a more subtle question, and historically it was an important one. In the early days of cosmic ray physics, some scientists did wonder whether there might be some unknown effect of velocity on particle stability. Maybe fast-moving particles are somehow harder to destroy, more robust, less likely to decay. But this idea has a problem. There's no mechanism in classical physics that would produce such an effect. In classical mechanics, the internal properties of an object don't depend on how fast it's moving. A clock runs at the same rate whether it's sitting on your desk or flying through space. A bomb fuse burns at the same speed whether the bomb is stationary or hurtling forward at 1,000 kilometers per hour. The internal processes of an object are independent of its overall motion. This is actually a deeply held principle of physics, the principle of relativity itself, which long predates Einstein. Galileo articulated it in the 17th century. If you're in a smoothly moving ship with no windows, there's no experiment you can perform inside the ship that will tell you whether you're moving or at rest. Drop a ball and it falls straight down. Pour water and it fills a glass normally. Toss a coin and it arcs through the air exactly as it would on land. Every physical process inside the ship proceeds identically whether the ship is docked in harbour or sailing at full speed across a calm sea. The laws of physics are the same in all uniformly moving reference frames. This means a muon's decay process, which is governed by the weak nuclear force, should proceed at the same rate, regardless of how fast the muon is moving. At least, that's what you'd expect from classical physics. The muon doesn't know it's moving. From the muon's own perspective, it's at rest, floating in its own little bubble of space, its internal processes ticking along at the only rate they know. Its internal clock should tick at its normal rate. And indeed, when muons are produced at rest or at low speeds in laboratories, they decay with the expected 2.2 microsecond lifetime. The lifetime doesn't depend on direction of travel, on temperature, on electric or magnetic fields, or on anything else you might think could influence it. The decay is governed by quantum mechanical probabilities that are intrinsic to the particle. You can't speed it up or slow it down by any classical means. The muon decays when it decays, and on average that's after 2.2 microseconds in its own reference frame. So all three escape routes fail. The muons are created high up. The production altitude is well established by decades of balloon and aircraft measurements going back to the 1930s. New muon production at lower altitudes doesn't explain the excess because it's already included in the models, and doesn't come close to accounting for the discrepancy. And there's no classical mechanism for extending a particle's lifetime based on its velocity. Every obvious classical explanation has been considered and eliminated. The prediction stands, and it's catastrophically wrong. If the muon's lifetime is truly 2.2 microseconds in all reference frames, if time is truly absolute and universal as Newton and every physicist before Einstein believed, then the flood of muons at sea level is simply unexplainable. Something foundational must be wrong with the classical picture. Not a detail, not a fine point. Something fundamental about how time and distance work at high speeds. This brings us to the historical experiments that made the discrepancy impossible to ignore. The most important of these was conducted in 1941 by Bruno Rossi and David Hall. Rossi was an Italian-born physicist who had fled fascist Italy in 1938 as anti-Jewish laws made it impossible for him to continue his work. He settled in the United States and continued his pioneering research on cosmic rays. Hall was an American physicist working alongside him. Together, they designed an experiment that was elegant in its simplicity and devastating in its implications. They measured the muon flux at 2 different altitudes and compared the results to the predictions of both classical physics and special relativity. Their experiment was conducted on Echo Lake in Colorado, at an altitude of about 3,240 meters above sea level, and at a lower site in Denver, at about 1,616 meters. The vertical distance between the 2 sites was about 1,624 meters. By measuring the number of muons arriving at each site with the same type of detector, they could determine what fraction of muons survived the journey between the 2 altitudes. The classical prediction was straightforward. Given the muon's 2.2 microsecond lifetime and the speed at which muons travel, you can calculate how many should survive a descent of 1,624 meters. The expected survival rate based on the classical lifetime was much lower than what Rossi and Hall actually measured. Significantly more muons were reaching the lower altitude than the classical calculation predicted. The muons were living longer than they should, or equivalently, they were traveling farther than their lifetime should allow. The numbers only made sense if you assumed that the muon's lifetime, as measured by the ground-based observers, was substantially longer than 2.2 microseconds. Not because the muon's internal clock was ticking at a different rate in any absolute sense, but because the muon was moving so fast that something about the relationship between its time and the observer's time had changed. Rossi and Hall's result was consistent with the predictions of Einstein's special relativity, published 36 years earlier. According to relativity, a muon moving at 99.8% of the speed of light would have its lifetime dilated by a factor of about 15.8, as measured by a stationary observer. That would stretch its apparent lifetime from 2.2 microseconds to about 34.8 microseconds, and its expected travel distance from 660 meters to roughly 10,400 meters. That's much closer to the 15 kilometers that the muons actually need to traverse. And when you account for the spread of muon energies, with some muons moving even faster than 99.8% and experiencing even greater time dilation, the predicted flux at sea level matches the observations beautifully. But Rossi and Hall's experiment, while convincing, had some limitations. The altitude difference between their 2 measurement sites was modest, only about 1,600 meters, and they couldn't directly measure individual muon velocities. They measured fluxes, the total rate of muon arrivals, and compared them to predictions. The comparison required assumptions about the muon energy spectrum, the production altitude, and other factors that introduced uncertainties. A more definitive experiment was performed 22 years later, in 1963, by David Frisch and James Smith at the Massachusetts Institute of Technology. This experiment is considered one of the cleanest and most convincing demonstrations of relativistic time dilation ever conducted. What made it special was its directness. Instead of comparing fluxes and relying on models, Frisch and Smith directly measured the number of muons at two altitudes and compared the observed decay rate to the relativistic prediction. They set up muon detectors at the top of Mount Washington in New Hampshire at an altitude of about 1,910 meters and at sea level in Cambridge, Massachusetts. The vertical distance between the two sites was about 1,910 meters. Their detectors were designed to select muons traveling within a specific range of speeds, roughly 99.5% of the speed of light. By selecting muons in a narrow speed range, they could make precise predictions about how many should survive the trip from mountaintop to sea level under both classical and relativistic assumptions. The results were striking. At the top of Mount Washington, they detected a certain flux of muons in their selected speed range. Classical physics predicted that the vast majority of these muons should decay during the roughly 6.4 microsecond journey from the mountaintop to sea level. Only about 27 muons per hour should survive. But the relativistic prediction, accounting for time dilation at 99.5% of the speed of light, predicted a much higher survival rate. About 412 muons per hour should make it. What did they actually measure? About 412 muons per hour. The agreement with the relativistic prediction was nearly perfect. The classical prediction was off by more than a factor of 15. There was no ambiguity, no room for reinterpretation, no possibility that some systematic error could account for the difference. 15 times more muons were surviving than classical physics allowed. The experiment left essentially no room for doubt. Time dilation was real. The muons clock was running slow, exactly as Einstein's equations predicted, and that was why so many muons survived the journey to the ground. The universe was behaving precisely as special relativity demanded, and the muon had become the messenger that proved it. Frisch and Smith also did something particularly clever. They filmed their experiment and produced an educational film that was widely distributed to physics departments around the world. It became one of the most famous physics demonstration films ever made, used in classrooms for decades to teach students that relativity isn't some abstract mathematical curiosity. It's a real, measurable effect that can be demonstrated with equipment on a mountaintop and a counter at sea level. But there's something important to emphasize here. Something that gets to the heart of what makes this result so profound. The muon doesn't know it's experiencing time dilation. From the muon's own perspective, nothing unusual is happening. The muon is born, it lives for about 2.2 microseconds, and it decays. Its internal clock ticks at the normal rate. Its decay process proceeds exactly as it would if the muon were sitting still. The muon doesn't experience its lifetime as extended. It doesn't feel like it's living longer. From the muon's point of view, its life is exactly as brief as any muon's life ever is. The time dilation is apparent only to us, the observers on the ground who are watching the muon zip past at nearly the speed of light. From our perspective, the muon's clock is running slowly. We see the muon living longer than 2.2 microseconds. We see it traveling farther than 660 meters. We measure its lifetime as dilated, stretched, extended by a factor determined by its speed. But this isn't because something is physically happening to the muon's internal machinery. It's because time itself is different for objects moving at different speeds. Time is not absolute. It's not the same for everyone everywhere. It flows at different rates depending on relative motion. And this isn't a philosophical statement or a matter of interpretation. It's a measurable, quantifiable, experimentally verified, physical fact. This raises a natural and important question. If the muon doesn't experience time dilation from its own perspective, if its lifetime is still 2.2 microseconds in its own reference frame, then how does the muon explain its own survival? From the muon's point of view, it lives for 2.2 microseconds and can travel only about 660 meters. So how does it reach the ground? The muon can't experience time dilation because it's always at rest relative to itself. Something else must be happening in the muon's frame of reference to explain how it covers a distance that should be impossibly large. And there is something else. But it's equally strange, equally counterintuitive, and equally well confirmed by experiment. If time is dilated for the moving muon as seen by the ground observer, then from the muon's perspective, something else must give. And what gives is space itself. From the muon's frame of reference, the distance to the ground is not 15 kilometers. It's much shorter. The atmosphere is compressed. The distance contracts, and this phenomenon, called length contraction, is the flip side of time dilation. Both are consequences of the same underlying physics, Einstein's special theory of relativity. Both are required for the universe to be self-consistent. And the muon, this tiny unstable particle raining down from the sky, demonstrates both of them simultaneously. The moon reaching the ground is not just a puzzle with an answer. It's a window into the deep structure of space and time. It tells us that the universe operates according to rules that are fundamentally different from what our everyday intuition suggests. It tells us that time is flexible, that distance is negotiable, that the relationship between the two depends on how fast you're moving. These aren't metaphors or poetic exaggerations. They're literal descriptions of physical reality, confirmed by experiment after experiment for over a century. And it tells us all this not through abstract mathematics or thought experiments conducted in the privacy of a theorist's office, but through a simple, measurable, repeatable fact that anyone with the right equipment can verify. Muons are created high in the atmosphere. They have short lifetimes, and they reach the ground in enormous numbers. The explanation for this fact requires us to abandon some of our deepest assumptions about the nature of reality. And that explanation, the full machinery of how relativity makes the impossible possible, and why both the ground observer and the muon itself agree on the outcome, despite disagreeing about the reasons, is where we turn next. To understand how muons survive their journey to the ground, we need to understand something that Albert Einstein published in 1905, when he was 26 years old and working as a part-time clerk in Bern, Switzerland. The paper was called On the Electrodynamics of Moving Bodies, and it laid out the special theory of relativity. The theory rested on two postulates, two assumptions that Einstein took as starting points and then followed wherever the mathematics led. The first postulate was that the laws of physics are the same in all inertial reference frames. An inertial reference frame is one that's moving at a constant velocity, not accelerating, not rotating, just coasting along at a steady speed in a straight line. This was essentially Galileo's old principle of relativity, extended to include not just mechanics but all of physics, including electromagnetism and optics. The second postulate was more radical. It stated that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This sounds innocuous, but it's actually revolutionary. It means that if you're standing still and someone drives past you at half the speed of light while shining a flashlight forward, you and the driver will both measure the light from that flashlight as traveling at exactly the same speed, 300,000 kilometers per second, not 300,000 plus half of 300,000, just 300,000, the same speed for both of you. This seems impossible. In everyday life, speeds add. If you're on a moving train and throw a ball forward, the ball's speed as seen by someone on the ground is the train speed plus the ball speed. But light doesn't follow this rule. Light always moves at light speed, regardless of who's watching and how fast they're moving. Einstein didn't just assert this, he showed that it was a necessary consequence of Maxwell's equations of electromagnetism, where the speed of light appears as a constant that doesn't depend on the reference frame. Einstein took this seriously and asked what the consequences would be if the speed of light were truly the same for all observers. The consequences were staggering. If the speed of light is the same for everyone, then something else has to give. Speed is distance divided by time. If two observers moving relative to each other both measure the same speed of light, then they must be measuring different distances or different times or both. And that's exactly what happens. Time and space are not absolute. They're relative. They depend on the motion of the observer. This is the heart of special relativity. Not that everything is relative in some vague philosophical sense, but that specific measurable quantities, time intervals, and spatial distances are different for observers in different states of motion. And the differences are not random or unpredictable. They follow precise mathematical rules encoded in a set of transformations called the Lorentz transformations, named after the Dutch physicist Hendrik Lorentz, who had worked out the mathematics a few years before Einstein, though without fully understanding their physical meaning. The key quantity in these transformations is called the Lorentz factor, usually represented by the Greek letter gamma. The Lorentz factor depends on the speed of the moving object relative to the observer. It's calculated as 1 divided by the square root of 1 minus v squared divided by c squared, where v is the object's speed and c is the speed of light. At everyday speeds, the Lorentz factor is essentially 1. If you're walking at 5 kilometers per hour, the deviation from 1 is so incredibly tiny that it's utterly unmeasurable. Your time runs at the same rate whether you're walking or standing still, for all practical purposes. But as speeds approach the speed of light, the Lorentz factor grows dramatically. At 50% of the speed of light, gamma is about 1.15. At 90%, gamma is about 2.3. At 99%, gamma is about 7.1. At 99.9%, gamma is about 22.4. And at 99.99%, gamma is about 70.7. The closer you get to the speed of light, the larger the Lorentz factor becomes, and it approaches infinity as you approach light speed. This is why nothing with mass can reach the speed of light. The Lorentz factor going to infinity means the energy required also goes to infinity. You'd need infinite energy to accelerate any massive object to the speed of light. It's not a matter of building a bigger engine, it's a fundamental mathematical impossibility. Now let's apply this to our muon. A typical atmospheric muon detected at sea level is travelling at about 99.8% of the speed of light. Let's calculate the Lorentz factor. We take 1 minus the square of 0.998, which gives 1 minus 0.996004, which is 0.003996. Take the square root of that, which gives about 0.0632. And 1 divided by 0.0632 gives a Lorentz factor of about 15.8. This number, 15.8, is the key to everything. It tells us exactly how much time dilation a muon experiences at this speed. And it tells us exactly how much length contraction the muon sees. Let's take each reference frame in turn and show how both the ground observer and the muon itself arrive at the same conclusion. The muon reaches the ground, but they explain it in completely different ways. First, the ground observer's perspective. You're standing on the surface of Earth with a muon detector. You look up. 15 kilometers above you, a charged pion has just decayed and produced a muon, traveling downward at 99.8% of the speed of light. You know that the muon's intrinsic lifetime is 2.2 microseconds. That's how long it lives in its own rest frame. But the muon isn't at rest relative to you. It's moving at nearly the speed of light. And according to special relativity, a moving clock runs slow as seen by a stationary observer. The muon's internal clock, the quantum mechanical process that governs its decay, appears to you to be ticking more slowly than normal. Specifically, the muon's observed lifetime is its rest frame lifetime multiplied by the Lorentz factor. 2.2 microseconds multiplied by 15.8 gives about 34.8 microseconds. From your perspective on the ground, the muon lives not for 2.2 microseconds, but for 34.8 microseconds. Its clock is running about 16 times slower than it would be if the muon were sitting still in your laboratory. How far can the muon travel in 34.8 microseconds at 99.8% of the speed of light? Multiply the speed by the dilated time. 299,400 kilometers per second multiplied by 34.8 times 10 to the negative 6 seconds gives about 10,400 meters. That's 10.4 kilometers. And remember, the Lorentz factor of 15.8 is calculated for a muon at 99.8% of light speed. Many muons are traveling even faster. A muon at 99.9% of the speed of light has a Lorentz factor of about 22.4, giving it a dilated lifetime of about 49 microseconds and an expected travel distance of about 14.7 kilometers. That's almost exactly the 15 kilometers from production altitude to sea level. And muons at 99.95% of light speed have an even larger Lorentz factor, about 31.6, and can travel over 20 kilometers before decaying. When you account for the full spectrum of muon energies produced in cosmic ray showers, with some muons traveling at 99.5% of light speed and others at 99.99%, the predicted number of muons surviving to sea level matches the observed flux beautifully. The calculation works. Time dilation, applied consistently across the distribution of muon speeds, explains exactly why 10,000 muons per square meter per minute reach the ground instead of essentially zero. From the ground observer's perspective, the explanation is clear. The muons live longer because their clocks are running slow, not because anything has physically changed about the muon's decay mechanism, but because time itself passes more slowly for objects moving at relativistic speeds. The muon's 2.2 microsecond lifetime is stretched by the Lorentz factor into a much longer observed lifetime, long enough for the muon to traverse the full depth of the atmosphere. Now, here's where it gets truly fascinating. Let's switch to the muon's perspective. This is the part that trips people up, and it's also the part that reveals something deep and beautiful about the structure of space-time. From the muon's own frame of reference, it's not moving at all. The muon is at rest. It's the Earth that's rushing upward toward it at 99.8% of the speed of light. In the muon's frame, its own internal clock ticks at the normal rate. It lives for 2.2 microseconds, just as any muon does. There's no time dilation from the muon's own perspective, because in its own frame, it's stationary. Stationary clocks aren't dilated. The muon experiences a perfectly normal 2.2 microsecond lifetime. But wait, if the muon lives for only 2.2 microseconds and can travel only about 660 meters in that time, how does the ground reach the muon? The ground is 15 kilometers away in the frame of the ground observer. If the Earth is rushing toward the muon at 99.8% of the speed of light, shouldn't it take about 50 microseconds for the ground to reach the muon? And the muon only lives for 2.2 microseconds. Shouldn't the muon decay long before the ground arrives? This is where length contraction enters the picture. According to special relativity, objects that are moving relative to an observer are contracted along the direction of motion. They're shorter than they would be at rest, and this contraction is governed by the same Lorentz factor that governs time dilation. The moving object's length is its rest length divided by gamma. From the muon's perspective, the Earth is rushing upward at 99.8% of the speed of light. The atmosphere, which is 15 kilometers thick in the Earth's rest frame, is contracted. Its thickness in the muon's frame is 15 kilometers divided by 15.8, which gives about 949 meters, less than a kilometer. The entire atmosphere, from the muon's birth altitude to the ground, is compressed into a distance of less than 1 kilometer as seen by the muon. Can the muon travel 949 meters in 2.2 microseconds at 99.8% of the speed of light? Let's check. In 2.2 microseconds, at that speed, the muon can cover about 660 meters, and 949 meters divided by 660 meters is about 1.4 mean lifetimes. The survival probability after 1.4 lifetimes is raised to the negative 1.4, which is about 0.25, 25%. One muon in 4 survives. That's an enormously different result from the 1 in 10 billion we calculated under classical assumptions. And when you account for the full range of muon energies, with faster muons seeing even more length contraction and therefore even shorter distances to the ground, the numbers match the observed flux at sea level. The muons explanation and the ground observer's explanation give the same answer. Both predict the same number of muons reaching the ground. This is the deep beauty of special relativity. The two frames of reference tell completely different stories about what's happening, but they agree perfectly on the outcome. The ground observer says the muon's clock runs slow, so it lives long enough to travel 15 kilometers. The muon says the atmosphere is contracted, so the distance is less than a kilometer, and its normal lifetime is sufficient. Different explanations. Same result. Both are equally valid. Neither is more correct than the other. They're just different perspectives on the same physical reality. This agreement isn't a coincidence. It's built into the mathematics of special relativity. The Lorentz transformations ensure that all observers, regardless of their state of motion, agree on physical outcomes. They might disagree about distances and times, and even about the order of certain events, but they always agree on things that actually happen. If a muon reaches the ground and triggers a detector, every observer agrees that the muon reached the ground and triggered the detector. They might disagree about how long the journey took, or how far the muon traveled, or how long the muon lived, but they agree that it arrived. The physical event, the muon hitting the detector, is an invariant fact that's the same in all reference frames. This consistency is what makes relativity a coherent theory rather than a collection of contradictions. You might think that if different observers measure different times and different distances, the theory would lead to paradoxes, but it doesn't. Every apparent paradox can be resolved by carefully applying the Lorentz transformations and remembering that time and space are intertwined in a four-dimensional structure called space-time. Events that are separated in space and time in one frame are separated by different amounts of space and time in another frame, but the space-time interval between them, a quantity that combines space and time in a specific mathematical way, is the same for all observers. It's like how a diagonal line drawn on a piece of paper has a certain length. If you rotate the paper, the line's horizontal and vertical components change, but the total length stays the same. Space-time works similarly. Time dilation and length contraction are like rotations in space-time. They change the individual components, how much time versus how much space, but they preserve the overall space-time interval. The muon demonstrates this beautifully. In the ground frame, the muon travels a large distance over a long, dilated time. In the muon's frame, the muon travels a short, contracted distance over a short, normal time. The space-time interval between the muon's creation and its arrival at the ground is the same in both frames. The physics is consistent. Reality is self-consistent. And a tiny unstable particle proves it every single second of every single day. Let me put this in broader context, because the muon's journey is not just a clever physics problem. It's one of the most important experimental confirmations of special relativity that exists. And it's happening all around you, all the time, without any human intervention or apparatus. You don't need a particle accelerator to see relativity in action. You don't need a billion-dollar laboratory. You just need a muon detector and a mountaintop. Or, even simpler, you just need to know that moons exist at sea level. That single fact, that moons reach the ground, is by itself a proof of special relativity. Because without time dilation and length contraction, they simply can't make the journey. Their presence at the surface is the proof. Every muon that passes through your body is a messenger from Einstein's equations, a physical confirmation that space and time are not what they seem. There are other confirmations of special relativity, of course. Particle accelerators routinely observe time dilation in unstable particles. The Large Hadron Collider at CERN produces muons, pions, kaons, and many other unstable particles at enormous energies, and their measured lifetimes are always consistent with relativistic predictions. But the muon holds a special place among these confirmations for several reasons. First, the effect is large. We're not talking about tiny corrections of a few nanoseconds per day, as with GPS. We're talking about a factor of 16 or more in the muon's observed lifetime. The time dilation is dramatic, impossible to miss, and impossible to explain away. Second, the experiment is simple. You measure muon rates at 2 altitudes and compare. No billion-dollar accelerator required. Frisch and Smith did it with equipment that could fit in the back of a truck. Third, and perhaps most importantly, the muons are natural. They're not produced by human technology. They're produced by cosmic rays hitting the atmosphere, a process that's been going on since before Earth existed. Relativity isn't something that only happens in laboratories. It's woven into the natural fabric of the world. Every time a cosmic ray strikes the atmosphere and produces a muon that reaches the ground, the universe is running an experiment in special relativity. And the result is always the same. Einstein was right. There's also something poetic about the muon's journey when you think about it carefully. Consider where that muon came from. Trace it back. A cosmic ray proton, probably accelerated by a supernova shockwave thousands or millions of years ago, traveled across the galaxy at nearly the speed of light. It crossed light years of empty space, dodging magnetic fields, threading through the interstellar medium, surviving for perhaps millions of years. Eventually it arrived at Earth. It entered the upper atmosphere and collided with a nitrogen nucleus at an altitude of 20 kilometers. The collision produced a spray of pions. One of those pions decayed into a muon. That muon, born in an instant of violence high above the ground, immediately began its race against its own mortality. It had 2.2 microseconds to live, a lifetime so brief that it challenges the meaning of the word. But it was moving at 99.8% of the speed of light. And because of the way the universe works, because of the deep relationship between space and time that Einstein uncovered, the muon's clock ran slow from the perspective of the ground. Or equivalently, the distance to the ground was compressed from the muon's perspective. Either way you look at it, the muon survived. It passed through the atmosphere. It passed through the roof of a building. It passed through the body of a person who didn't feel a thing. And then it decayed, silently, invisibly, transforming into an electron and 2 neutrinos that scattered into the world. That journey from a dying star to an atmospheric collision to a relativistic race to the ground is happening above your head, thousands of times per second. Each muon is a tiny messenger carrying information about particle physics, about cosmic rays, about the structure of space-time, about the fundamental laws that govern the universe, and each one proves, simply by arriving at the ground, that time is not absolute. This leads to a question that people sometimes ask, and it deserves a clear answer. If time dilation makes the muon live longer from our perspective, does that mean time travel is real? In a sense, yes, but not in the way science fiction usually portrays it. You can't use time dilation to travel backward in time. You can't go back and change the past. But you can travel forward in time faster than normal. If you could somehow travel at 99.8% of the speed of light, like a muon, time would pass 16 times more slowly for you than for people on Earth. You would age 1 year while they age 16 years. You would, in effect, be traveling into their future. When you stopped and looked around, you'd find that the world had aged 16 years for every 1 year you experienced. This isn't theory, it's physics. It's what happens to muons. They travel into our future, living far longer in our frame than in their own. Astronauts on the International Space Station experience a tiny version of this. The station orbits Earth at about 7.7 kilometers per second. At that speed, the Lorentz factor differs from 1 by less than a billionth. Essentially 1, but not exactly 1. Astronauts on the station age very slightly less than people on the ground. Over a 6-month mission, the difference accumulates to roughly 5 milliseconds. Not enough to notice, but enough to measure. Astronaut Scott Kelly, who spent 340 days on the station, came back about 9 milliseconds younger than his twin brother Mark. He traveled 9 milliseconds into Mark's future. The effect is real, measurable, and perfectly consistent with special relativity. The muon just does it on a much grander scale because it's moving so much faster. But let's return to the ground, to you, standing here under a sky that's raining muons. Let me leave you with the full picture of what's happening right now. Above your head, cosmic rays are striking the atmosphere. They've been doing this for 4.5 billion years. Since before the Earth had oceans, since before the first living cell appeared. These cosmic rays come from supernova remnants, from the spinning remnants of dead stars, from the violent hearts of distant galaxies. They carry energies that dwarf anything human technology has produced. When they hit the thin air of the upper atmosphere, they create cascades of particles. Among these particles are pions, which almost immediately decay into muons. These muons are born at altitudes of 15 to 20 kilometers, traveling at more than 99% of the speed of light. Their lifetimes are 2.2 microseconds. Classical physics says they should decay in less than a kilometer. They should never reach you. But the universe doesn't follow classical rules at these speeds. At 99.8% of the speed of light, space-time itself bends to accommodate the muon's journey. From your perspective, the muon's clock runs slow, stretching its brief lifetime by a factor of 16. From the muon's perspective, the atmosphere is compressed, shrinking the 15-kilometer gap to less than 1 kilometer. Both descriptions are correct. Both are incomplete without the other. Together, they form a single, consistent picture of a universe where time and space are woven together into a flexible, dynamic fabric that responds to motion. And so the muon arrives, 10,000 of them per square meter per minute, passing through buildings, through mountains, through the bodies of every person on Earth, leaving no trace, causing no harm, carrying within their survival a proof of one of the deepest truths physics has ever uncovered. That time is not a river flowing at a constant rate. Time is elastic. It stretches and compresses depending on how fast you move through space. The faster you go, the more time bends. And at the speeds these muons travel, it bends enough to turn an impossible journey into an ordinary event. The muon is a humble particle. It's not as famous as the electron. It doesn't form atoms or carry electrical current or make chemistry happen. It was unexpected when discovered, unwanted when identified, and for decades it seemed purposeless. Who ordered that? Rabbi asked. But the muon has given us something no other particle provides quite so cleanly. It gives us a natural, continuous, free demonstration that special relativity is not an abstraction. It's not a mathematical curiosity. It's the actual operating system of the universe. Every muon that passes through your body is whispering a truth about the nature of reality. Time is not what you think it is. Distance is not what you think it is. And the universe is stranger, more flexible, and more beautiful than everyday experience could ever suggest. The next time it's a clear night and you look up at the sky, think about what's happening in the invisible space between you and the stars. Think about the cosmic rays arriving from across the galaxy, striking the atmosphere, producing cascades of particles, creating muons that race downward at nearly the speed of light. Think about how those muons should die before they reach you, but they don't. Because the universe runs on Einstein's rules rather than Newton's. Think about how time dilation and length contraction, two consequences of a theory published by a 26-year-old patent clerk in 1905, are the only reason those particles survive long enough to reach the ground. And think about the fact that this is happening right now. Not in some distant future or far-off laboratory. Right now, as you listen to this, muons are passing through you at this very moment, each one a tiny proof that space and time are intertwined, that the speed of light is absolute, and that the universe is far more extraordinary than it appears. You are bathed in proof. You are surrounded by evidence. Every second, thousands of tiny unstable particles pass through your body. Particles that have no business being here. particles that should have vanished long before reaching the ground. They survive because time bends. They arrive because space contracts. And they prove, silently and continuously and without any human effort, that the universe we live in is a relativistic universe, Einstein's universe. A universe where nothing is quite what it seems at first glance, but where everything, once you understand the rules, makes perfect, elegant, astonishing sense. That's what a muon really is. Not just a particle. A proof. A tiny, fleeting, beautiful proof that the deepest truths about the cosmos are written in the fabric of space-time itself, and that even the most short-lived, seemingly insignificant things can carry messages of extraordinary importance. The muons will keep falling tonight, and tomorrow night, and every night after that. And each one will whisper the same truth. Time is relative, space is flexible, and the universe is more wonderful than you ever imagined. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the science that shapes our universe. Remember, those muons are passing through you right now. Tens of thousands every minute, each one proof that space and time are not what they seem. The universe is telling you something extraordinary. All you have to do is listen. Good night.